Hi friends, welcome to my YouTube channel. So today friends, we are going to start a very new chapter on structural analysis. So I know that many people have many doubts regarding structural analysis, and we have many methods to calculate the analysis of an indeterminate structure. So here I am starting with a very small topic which is called as moment distribution method. So here comes our chapter 2, moment distribution method. So I'll be just giving you a very brief introduction or like a very simple problem how to do a moment distribution with a two-span beam. So friends, if you have any doubts or any further problems you need for the same, you can put a comment in the comment box and let's get started. So here is a question. We have the question, analyze a given beam and draw the bending moment diagram. And here we have a beam ABC, wherein AB is having a UDL and BC is having a point load. And you know that from the figure, the point load is not exactly at the middle of the beam. It is having a distance of 2 meters from the left and 3 meters from the right. And you have a UDL of 30 kilonewton per meter for the span AB. So the very first step whenever you get a problem is to find your fixed end moment. So your step 1 is fixed end moment. So here you're going to calculate the fixed end moment for the spans AB and BC. So in your span AB, there are two members, one starting from A towards B and the other one starting from B towards A. So you have the fixed end moment for MFAB, MFBA, and similarly for the BC span you have for BC and CB. So AB means starting from A towards B and MFBA means starting from B towards A. MFBC means starting from B towards C and the same for CB. So whenever you have a UDL, please keep in mind the fixed end moment for a fixed beam which is having a UDL is WL square by 12. And always you have a negative value for the left hand side and the positive value for the right hand side. So since your A is on to the left and B is on to the right, your MFAB is minus WL square by 12 for the left hand side and plus WL square for the right hand side. I have many other videos which will be elaborately telling you how you got this value. Again, you can keep a comment in the comment box so that I'll be keeping a new video regarding how this values came. Now, when you calculate the load is 30 and the span is 6, you're going to get the fixed moment as minus 90 and plus 90 kilonewton meter for the span AB and BA. So similarly, we are going to find it for the span BC and CB. So here also, that's a small mistake. It's actually minus WAB square by L square and WA square B by L square. Now here is the next thing. A is nothing but the left side of the beam and B is nothing but the right side of the point load. So when you consider the span AB, the left hand side of the load is 2. So that is taken as A, and the right hand side of the load is 3, which is taken as B. So the load is 40 into 2 into 3 square divided by the total length is 5 meter, 5 square. And for the second one, WA square B by L square, which again you are getting it as 19.2. So here also you are getting the two other values. Now we are going to the second step. Now the second step is distribution factor. Friends, you should be very careful. This is the method with whichever problem you get or whatever type of load you are getting, this is the fundamental. The only thing that is going to change is the type of support and the type of loading. But once you understand the basics, the concept is going to be absolutely same. So let's get started with your step 2, which is nothing but your distribution factor. So here, before going to your step 2, there is a two small note which is very easy for you to understand. That is, you consider a fixed beam like this. You consider a fixed beam like this. So here the stiffness is nothing but your I, which is your moment of inertia, divided by the length of the beam. Because obviously when you take a beam, if it is fixed in both the end, it has more stiffness. But what happens if you remove the fixity on one side, you get a pin or a hinge on the other side, you don't get the same fixed stiffness of a fixed beam. The stiffness will be obviously less. By how much percent it will be less? It will be less by 75%. Or it is nothing but if you are having a beam like this for the second case, it is 3 by 4 I by L. So now we are going to our problem. We are having ABC span. And here what I do is I have a box in which I have columns like joint, member, relative stiffness, total relative stiffness, distribution factor, and the beam figure. So again, the next shortcut is, what should you write in the column joint B? Joint is nothing but you are only considering the interior joint. So in your figure, if you have ABC, which is pinned or roller, let it be. So here your intermediate one is B and the extreme ones are A and C. So your intermediate joint is something which you are supposed to write it here. So here it is B. And what are the members that is originating from B? From B you have BA, and from B you have B to C. So that is a member BA and BC. And make sure that you are not writing AB and CB, because AB is nothing but that starts from A, not from B. So here again, what I have a small note again is that as an assumption, what we do is that whatever joint you write it in the column B, that is your intermediate joint, is just kept as a fixity for an assumption. So here what I do is I'll replace this hinge by a fixity just for an assumption purpose. Later I'll be compensating this assumption. So here I'm keeping joint B as fixate, and then what I do is I split the beam as AB and BC. So here you can see A is pinned, as I have not changed the support, but B in both the figures I have changed it to fixity. Now you consider, draw the same figure on the last portion, that is your beam figure. So here you have the figure like this and the figure like this. So here, if you consider this type of a figure, you can understand that since it's not fixed in both the ends, it is 3 by 4 I by L for both the cases. So for AB and BC span, you can see one side is pinned and one side is fixity. The stiffness for both the cases will be 3 by 4th time of I by L. So here I'm writing relative stiffness. Stiffness is nothing but the ability to withstand the load. So here it is 3 by 4 into I by L. L is the length of the span BA. So your length of the span BA is given as 6 meter in your question. So it is 3 by 4 into I by 6. You are getting 3 I by 24. Similarly for the span BZ, it is 3 by 4 I by 5, where 5 is the span length. So here you are getting 3 I by 20. Now your next column is total relative stiffness. That is, you consider the joint B. B is having a total stiffness of 3I by 24 and 3I by 20, making a total sum of 33I by 120. Now we calculate the distribution factor, denoted as DF. It is nothing but the ratio of their stiffness of a joint. That is, you are having the stiffness of BA as 3I by 24 and the total stiffness as 33I by 120. You're taking the ratio and you're getting it as 5 by 11. And for the second case, you are writing 3I by 20 as its individual stiffness and 33I by 120 as a total joint stiffness. You're getting it as 6 by 11. So this is your step number 2. Now we go on to step number 3. So here we come to the method of step 3, moment distribution method. So here is the next thing which you should be able to understand. You're writing the joints A, B, and C as given in the problem, and in your beam, you're having AB, BA, BC, and CB as your member. And make a small box near to joint B, or whatever you have written in your previous tabular column. If you're having BA and BC, it should have a box in the next place, writing it as 5 by 11 and 6 by 11, going for a ratio of 0.45 and 0.55. Another important thing, when you add the stiffness of BA and BC, you should always get the stiffness as 1. So here you just see 0.45 plus 0.55. When you add, you're going to get it as 1. Now what happens? Suppose if for BA it was 0.3, then what will be the value for BC? Yes, it will be 0.7. So that you're getting a sum of 1. So once you write your member names, next thing is you are supposed to write your fixed end moment. So here you are writing minus 90, plus 90, minus 28.8 and 19.2, which you got it from your step 1 fixed end moment. Now, before starting the moment distribution, you should be very careful with the type of support. So here, make sure whether you have any hinges in your beam other than your intermediate support. Yes, in your figure, your A and B are hinges. So you know the property of hinge is that hinge doesn't have a capability of taking the moment, or your moment capacity will be equal to 0. But here you're having AB as minus 90 and CB as 19.2, which you should make it as 0 before you start the moment distribution method. So here minus 90, what we do is that to make it to 0, I'm adding plus 90 to the joint AB. Similarly for the joint CB, I am adding minus 19.2 to compensate with your plus 19.2 so that your total value becomes equal to 0. So when you do something in one joint, you're supposed to give a partition or a partial amount to your neighbor. That means if you are giving plus 90, you have to transfer your half to your adjacent member BA as 45. And if you are giving minus 19.2 to CB, you should give your half the value to the value member BC, that is your minus 9.6. So once you get it, and now you add all the values, here you are having 0 for BA 135, BC minus 38.4, and in your joint CB, you're getting 0. Now it's your perfect method. See, this is your initial moment wherein your edges have become 0 and you made it 0. Why? Because you had a hinge there. If you had a fixity there, you can completely avoid this second step of releasing the extreme supports at A and C. We'll be discussing the same thing in your upcoming videos so that the doubt in this method will be completely cleared. And trust me friends, this will be the best method for your moment distribution method and you're never going to forget it. Now, once you write your initial moments, now here we are starting our moment distribution method. So now just see friends, in BA, you are having 135 and in your joint BC, you are having minus 38.4. So obviously, we know that in this case, there is some disturbances. That means in one place, you are not having the same value on the left and right hand side. So what happens is that they are not balanced. The joint BC and BA are not balanced. So here you can see that this side you're having 135. Here you're having 135 and here you're having minus 38.4. So there is what you tell it as, there doesn't have a proper equilibrium when you take these two values. So what you have to do is that you have to compensate the value, or you have to just make it as equal and opposite. So here on the right hand side, you can see that 135 is a clockwise moment and minus means it's an anti-clockwise moment. So there is a lump sum moment of 135 minus 38.4, you're having a lump sum moment of 96.6 on the right hand side. Here you can see this. So that is a lump sum moment which is getting accumulated in joint B. And we know that as per the problem, joint B is a hinge. It's an intermediate joint and it should have a net moment equal to 0. So to make it equal and opposite, that is BA and AB should be equal and opposite. What you do is that if it is having 96.6 as a lump sum moment, you take that 96.6 from the junction B, that is you're subtracting 96.6 from plus 96.6, so that what happens, minus 96.6 and plus 96.6 will be ultimately equal to 0. So this is nothing but the balanced value. You're putting minus 96.6 to compensate your lump sum moment, and whatever you are giving to the junction B to make it equal and opposite, that value will be equally shared by the two members based on their distribution factor. So here for for BA, you are having 5 by 11 and for BC, you are having 6 by 11 as the proportion. So they'll be sharing it as 45% for BA and 55% for BC for the value minus 96.6. So here you have minus 96.6 into 0.45, you're getting minus 43.5. And for BC, you're having minus 53.3, and make sure your sign convention is correct or else you're going to make mistake, my dear friends. So here what I do is that I'm writing minus 43.5 and minus 53.1 in BC and BA. And now the next step is your carryover. So actually what I'm supposed to do, this value I'm supposed to give half to your neighbor, but here I have already done the balancing in the beginning. So sorry, I have already done the carryover in the beginning. So you are not transferring this moment. So you can stop with this step and add the total moment as this side becomes 0. This side is 135 plus 43, you're getting plus 91.5. Here you're having minus 38 and minus 53, you're getting minus 91.5. And for the joint CB, you're having equal to 0. So this becomes your final moment. So I'll again clarify with the end that portion. That is, make sure if your net moment in the joint is positive, to balance it, you have to put negative. if your net lump sum moment is negative, to balance it, you have to put a positive sign. And that is how you are getting this negative 43 and negative 53. So once you have done it with this, you can add all the values right from the initial moment. Make sure you're supposed to start from the initial moment, and you should never take this top value because you have compensated this value and modified it as your initial moment. So your analysis starts from the initial moment, your balancing, and your carryover. So with this, you're getting your final moments. Now let's see how to draw the bending moment diagram. So we are going to your next step, which is nothing but your bending moment diagram. So till step 3, it is the same for almost all the problems, except that you have a small changes for the load and the type of span and the length of the span. Now next we go for the next step, step number 4. So now we go for your step number 4, which is your final moment. So here I am rewriting whatever value I got in your step 3 as 0, minus 91, plus 91, and your 0. Okay, sorry friends, there is a small change. It's 0 plus 91.5 minus 91.5 and 0. So here comes a small change. This becomes plus and this becomes minus. So now after drawing this, you're supposed to calculate your positive moments. So in your strength of material, you have already studied how to find your positive moment. Like if it's a simply supported beam with UDL, it's WL square divided by 8. And if it is a load, simply supported beam with a point load, WL by 4, and unsymmetrical load, WAV by L. So here, once you substitute WL square by 8, you're getting 135, and WAV by L, you're getting it as 48. So when you draw the diagram for AB span, it should be a parabola as shown in the figure. And for the BC span, it should be a point load with a straight line for BC span. So it's a triangle and a parabola. And after that, you're hatching the extra portion, which is given in the gray color. So this becomes your net bending moment diagram. Now there is again a very easy method. You call it as a pen technique, wherein we can draw the bending moment diagram for any beams, any value, just in 1 minute. So that I'll be explaining you in my next video. So my upcoming videos will be how to quickly draw the bending moment diagram and shear force diagram. That is a shortcut which you call it as a pen technique. And I have my upcoming videos like a 3-span continuous beam with the same moment distribution method. We have also videos coming for the topics slope deflection method, stiffness method, flexibility method, and your Canis method. So friends, if you like the video, you have to keep a small comment in my comment box. And if you like my video, you have to subscribe my channel and click the bell icon for my more notification, and please subscribe my YouTube channel. Also friends, if you are happy with the video and if you like the method in which I have taught you, please share it to your friends so that let it be a helping hand for the other people who doesn't know the moment distribution method. So thank you friends. See you in your next video. Bye.